Before we begin, let's take a moment to imagine something simple. Imagine you're holding a glass of water. Nothing fancy, just a clear glass filled from your kitchen tap. You swirl it a little, watch the light bend through it, maybe take a sip. It tastes ordinary, familiar, reliable. On Earth, water is just there. It runs from our faucets, floats in clouds above us, collects in rivers, and roars across the world's oceans. It's woven into our everyday routines so tightly that we barely notice how strange and rare it actually is. Or at least, that's what we used to think. For most of human history, people believed Earth was special because it had liquid water. In fact, that became one of the main reasons we thought life might only exist here. But something interesting has happened over the last few decades. As our spacecraft have traveled farther, our telescopes have sharpened, and our instruments have become more sensitive, we've discovered something that feels almost backwards. Earth is not the only world with oceans, and even more surprising, Earth might not have the most water at all. There are moons in our solar system, cold, distant, dimly lit worlds that hide more water than all of Earth's oceans combined. Some are wrapped in thick, protective ice. Others erupt through cracks as plumes. Some may have oceans so deep they make the Pacific look like a puddle. And beyond our solar system, orbiting stars light years away, there are exoplanets with signs of steam, clouds, and global seas. Worlds where water doesn't just exist, it dominates. Over the next some minutes, we're going to explore 4 of the most surprising ocean worlds we know of: Europa, Enceladus, Titan, and several exotic exoplanets that push the limits of what a water world can be. But before we dive into those places, this first chapter sets the stage, a calm and simple look at how we even discovered these hidden reservoirs in the first place and why they matter. Because once you understand where these oceans are hiding, you start to realize something important. Water might not be rare in the universe. Life might not be rare either, and the idea of an ocean world might be far more normal than we ever imagined. So let's begin with something familiar, our relationship with water, and slowly expand outward into the places where oceans wait in the dark. The first surprise was that Earth may not even be the most water-rich planet or moon around. When scientists started measuring the mass and density of certain moons in the outer solar system, they found something unexpected. Many of these worlds were lighter than rock alone would explain. Something less dense, something like water, had to make up a significant portion of their interiors. Then, as we flew spacecraft past them and captured higher resolution data, the mystery deepened. Some surfaces were smooth and cracked, like frozen lakes. Some had magnetic signatures that suggested liquid beneath. Some literally sprayed their ocean into space. The idea that water was rare suddenly fell apart. Take Europa, one of Jupiter's moons. Its frozen surface looks like a cracked eggshell, but beneath that shell lies an ocean believed to be deeper than all of Earth's oceans combined. And then there's Enceladus, a tiny moon of Saturn, which erupts with plumes of water vapor that our spacecraft have flown directly through. Or Titan, with lakes of liquid methane and a possible subsurface ocean of water and ammonia. And that's just our solar system. Beyond it, astronomers are now discovering planets where entire worlds might be covered in global oceans hundreds of kilometers deep. It turns out the universe is full of water, just not always in places where we can see it. You might wonder how we even discovered these hidden oceans. After all, we can't simply look through thousands of kilometers of ice. So scientists used a few clever methods. Gravity measurements helped reveal what lies beneath surfaces. When a spacecraft flies over a moon, It gets tugged slightly by that moon's gravity. The way the spacecraft wobbles tells us whether the moon's interior is uniform or if there are layers, such as a liquid ocean, shifting beneath the crust. Then came plumes. When Cassini flew past Enceladus, it detected geysers shooting up from cracks in the moon's icy shell. These geysers weren't just water vapor. They contained salt, organic molecules, and tiny particles that could only form in a warm ocean-touching rock. It was like the moon was leaking clues into space. And finally, spectroscopy, a method that allows us to read the chemical fingerprints of light. Using telescopes, we can detect water vapor, frozen water, and even signs of oceans hidden beneath thick atmospheres on exoplanets dozens or hundreds of light years away. All these tools together painted a simple but profound picture. Water is everywhere. Not just the flowing rivers we imagine, but planetary-scale reservoirs, oceans locked under ice, seas kept warm by tidal forces, global waters on planets so far away we can't even see their surfaces directly. So in this documentary, we're going to travel slowly, calmly, through some of the most intriguing water worlds we know. Not in a dramatic Hollywood disaster way, but in a grounded, natural way that lets the wonder speak for itself. We'll start with Europa, a moon that looks quiet on the outside, but hides a deep global ocean beneath an icy crust. An ocean so vast and so dark that if we could send a submarine down into it, we might find environments unlike anything on Earth. Then we'll visit Enceladus, the moon that literally sprays its ocean into space. Cassini flew through those plumes, tasted the ocean indirectly, and found signs that hydrothermal activity, the same kind that supports life in Earth's deep seas, might be happening there too. After that, we'll explore Titan, a world with clouds, rain, rivers, lakes, and seas, but not made of water. Titan's lakes are filled with liquid methane and ethane, while a possible water ammonia ocean waits far below the surface. It's an Earth-like world, but in a completely alien way. And finally, we'll go beyond the solar system to look at exoplanets, worlds where whole planets might be covered in water, or wrapped in steam atmospheres, or hiding warm oceans beneath layers of ice and rock. So, let's begin. Because if you think Earth's oceans are deep, wait until you hear what lies beneath the ice of Jupiter's moons. If you were drifting through space and happened to pass by Jupiter, Europa probably wouldn't be the first thing to catch your eye. Jupiter itself steals the show, a swirling giant with storms the size of planets and colors that look painted by some cosmic artist. But if you look a little closer, orbiting quietly nearby, you'd notice Europa, a small, bright moon, almost shy in comparison. Smooth, pale, and lightly cracked, it looks like a frozen pearl caught in Jupiter's enormous gravitational pull. Europa's surface is mostly ice, clean white ice that reflects sunlight like freshly fallen snow. But it's not a smooth sheet. When you look at photographs from spacecraft like Galileo, you see reddish-brown streaks crisscrossing the moon, like scars on a perfectly white canvas. These streaks aren't random. They're fractures, lines where the ice has split or shifted. Some stretch for hundreds of kilometers. Others twist and curl like a frozen riverbed. At first glance, they might seem chaotic, but they tell a story. Europa's surface may be still and silent today, but it's far from dead. Underneath that ice, the moon is moving and flexing, not the surface itself, but the ocean beneath it. Europa's icy shell is thought to be between 15 and 30 kilometers thick. That sounds enormous, and it is. But below that layer is where things become interesting. Because beneath the ice lies a global ocean that wraps around the entire moon. Imagine Earth's oceans, all of them combined. Now imagine an ocean with more water than that, hidden in darkness, stretching down perhaps 100 or even 150 kilometers deep. For comparison, the deepest spot in Earth's oceans, the Mariana Trench, is not even 11 kilometers deep. Europa's ocean might be 10 times deeper than anything on our planet. And what keeps this ocean liquid? It's not sunlight. Europa receives very little. It's not heat from the surface. The surface is colder than Antarctica's coldest night. The secret is tidal heating. Europa orbits Jupiter in an elliptical path, meaning the Moon moves closer and farther away during each orbit. As Europa changes distance, Jupiter's immense gravity tugs on the Moon, stretching it slightly. This constant flexing heats Europa from the inside, just like bending a paperclip back and forth warms it. Deep beneath the ice, the ocean stays warm enough to remain liquid, perhaps warm enough to host something even more exciting. But before we talk about life, it's worth understanding how we know all of this. After all, no one has drilled through Europa's ice. No submarine has swum through its waters. Everything we know so far comes from clever measurements and a few tantalizing clues. One of the biggest breakthroughs came from Europa's magnetic field. Jupiter has an enormous magnetic environment, like a giant bubble of magnetism. Europa sits inside this bubble, and as it moves, it interacts with Jupiter's field. Scientists noticed that Europa's magnetic signature behaved in a way that suggested a conductive layer beneath the surface. The best explanation? A global salty ocean, just like Earth's. Salt water conducts electricity, and Europa's ocean appears to be rich in dissolved minerals. Then came the images and data showing cracks, shifting patterns, and even surface features that look like ice spreading apart and refreezing. In some places, the ice appears thinner. In others, reddish materials that may come from the ocean below have seeped upward. And then there are the plumes. Maybe. In recent years, telescopes and spacecraft have detected what appear to be faint geysers erupting from Europa's surface, shooting water vapor dozens of kilometers into space. These plumes are not as dramatic as those on Enceladus, but if they're real, they represent direct samples of the ocean drifting into space. Scientists are still debating the evidence, but if confirmed, Europa would join the very small family of worlds where the interior ocean makes itself visible. All these clues point to one central idea. Beneath the quiet surface lies a restless, liquid world. And that leads us to the question everyone wonders about. Could Europa's ocean support life? The ingredients for life, as we understand it, include liquid water, an energy source, and the right chemical building blocks. On Earth, life thrives not just at the surface, but deep in the ocean, around hydrothermal vents, cracks where heat from Earth's interior meets cold seawater. Entire ecosystems survive there, completely independent of sunlight. Bacteria feed off minerals and chemical energy, and larger organisms grow on top of that microscopic foundation. Europa appears to have something similar. The tidal forces that heat the Moon might also drive volcanic or hydrothermal activity on the ocean floor, delivering warmth and nutrients into the water. If Europa has rocky seabeds, and it likely does, that means the ocean could be interacting with mineral-rich rock, creating a natural chemistry lab. It doesn't guarantee life, but it does make the possibility feel less like science fiction and more like a scientific question waiting to be answered. Sometimes it's fun to imagine dropping a submarine into Europa's ocean. What would it see? Darkness at first, a vast black nothingness stretching in every direction. But as the lights flick on, maybe you'd see drifting snow-like particles, organic material or minerals. Maybe you'd see plumes of heated water rising from vents. Perhaps even something more complex, moving slowly in the gloom, shaped by an ocean utterly unlike Earth's. We aren't there yet, but missions are coming. NASA's Europa Clipper, launching soon, will perform dozens of close flybys, mapping the ice, measuring the ocean, analyzing the chemistry, and searching for signs that Europa's ocean could support life. And while Europa is one of the most promising ocean worlds, it's not the only one. In fact, the next moon in our journey might be even more surprising, not just because it has an ocean, but because it practically sprays that ocean into space for us to study. Europa is exciting. But the next world might be even more surprising. If Europa is the ocean world that feels hidden and mysterious, then Enceladus is the one that practically waves its ocean in our face. And the funny thing is, Enceladus is tiny. It's one of the smallest major moons in the solar system, only about 500 kilometers across. To put that into perspective, it's smaller than many countries. You could fit Enceladus comfortably inside the state of Arizona. It's the kind of moon you might expect to be just another frozen rock drifting quietly around Saturn, cold and simple with not much going on. But Enceladus is a perfect example of why you shouldn't judge a world by its size. Despite being tiny, Enceladus somehow hides a global ocean beneath its icy shell, and not just any ocean. An ocean that is warm enough, active enough, and chemically rich enough to spray through cracks in its surface and into space. If Europa is a sealed vault of water, Enceladus is the opposite, a cracked sphere with a natural fountain at its south pole. The story of how we discovered this begins with NASA's Cassini spacecraft, a mission originally sent to study Saturn, but one that ended up revealing some of the most surprising secrets in the solar system. When Cassini first flew by Enceladus, it captured images of the moon's south pole that were strange. Instead of being smooth and cold like the rest of the surface, the South Pole was crisscrossed with long bluish fractures, later nicknamed tiger stripes. And near these stripes, Cassini's instruments detected something unexpected: heat. Heat on a moon this small, this far from the sun, didn't make sense. But then came the moment that changed everything. Cassini flew a little closer, and its cameras detected what looked like a faint, ghostly mist rising off the surface. A plume, and then another, and then dozens. Enceladus wasn't quiet at all. It was erupting. These weren't explosions or volcanic eruptions like we see on Earth. They were jets of water vapor, ice grains, salts, and organic molecules shooting out from beneath the surface and rising hundreds of kilometers into space. Imagine a world that constantly vents part of its ocean upward, like a natural spray bottle at a planetary scale. Scientists were stunned. It wasn't just that Enceladus had water. It was that the moon was actively giving us samples of it. We didn't need to drill, melt, or dig. The ocean was coming to us. Cassini flew through those plumes multiple times, and each time its instruments collected more clues about the hidden ocean below. It detected salt, suggesting that the ocean is in contact with rock, much like Earth's oceans. It found organic molecules, which are the building blocks of life. And, most intriguingly, Cassini found tiny silica particles, grains so small and so specific that they could only form in one kind of environment: hot water interacting with rock at high pressures. On Earth, silica like this forms at hydrothermal vents, deep-sea fissures where seawater meets volcanic rock, heating up and becoming rich in minerals. And here's the interesting part. Earth's hydrothermal vents are home to some of the most primitive and resilient forms of life we know. Whole ecosystems thrive there, completely independent of sunlight. Life powered by chemistry, not photosynthesis. So when Cassini found signs of possible hydrothermal vents on Enceladus, It raised a simple but profound question. If vents on Earth can support life, could vents on Enceladus do the same? Now, we don't know the answer yet. We haven't landed on Enceladus. We haven't sent a submarine down into its ocean. We haven't scooped up a sample and looked at it under a microscope. But the chemistry that Cassini found, water, heat, minerals, organics, checks a lot of the same boxes that Earth's early oceans did before life formed. It doesn't guarantee anything, but it places Enceladus high on the list of places where life could exist. And what's nice about talking about Enceladus is that it doesn't require wild imagination or giant leaps. The moon literally sprays its own evidence into space. If you wanted to study it, you could just send a spacecraft through the plumes again with more advanced instruments. It's like Enceladus is doing half the work for us. The idea of an entire ocean under such a tiny moon feels almost like a cosmic trick. But this is where planetary science becomes humbling. The places with the best ingredients for life might not be warm, Earth-like planets. They might be small, icy worlds heated by tidal forces and internal energy, quiet on the outside, but full of activity beneath. If life exists anywhere beyond Earth, there's a very real chance that it could be swimming around in an ocean like the one under Enceladus's crust. Maybe forming near warm vents, maybe drifting through darkness, maybe simple, maybe complex. We don't know yet, but we know enough to keep looking. And as promising as Enceladus is, it isn't the only fascinating moon of Saturn. There's another one, bigger, thicker, and much stranger. A moon with rivers and lakes on its surface, clouds in its sky, and possibly another ocean hidden far below. A world that looks a little like Earth if you squint, but behaves nothing like it once you get closer. If Enceladus has an ocean full of ingredients for life, then Titan offers something entirely different. If Europa and Enceladus feel mysterious because everything happens beneath their icy shells, Titan is almost the opposite. Titan wears its strangeness openly. When you first see an image of this moon, Saturn's largest, it doesn't look sharp or reflective like Europa. Instead, Titan looks hazy, wrapped in a thick orange atmosphere that makes it feel surprisingly familiar, almost like a blurry photograph of early Earth. And that's the first thing that stands out about Titan. It has an atmosphere thicker than Earth's. Not just a thin whisper of gas like most moons, but a dense, heavy atmosphere made mostly of nitrogen. If you were standing on Titan's surface, wearing proper gear of course, the air pressure around you would feel very similar to the ground level pressure here at home. You'd also notice something else. The light is dim and golden, filtered through a permanent orange haze. The sun would look like a bright dot instead of a disk, but the mood would be strangely calming, almost like watching a sunset that never ends. For a world so far from the sun, Titan is remarkably active. It has weather, real weather, clouds, winds, storms, and even rain, but not water, rain. Titan's rain is made of liquid methane and ethane, falling from hydrocarbon clouds in slow, gentle drops. These drops carve out river channels on the surface, filling lakes and seas that pool across the northern hemisphere. When you look at radar maps from the Cassini spacecraft, you can see entire coastlines and branching river systems. If you didn't know better, you might think you were looking at Earth, until you remember these lakes are made of liquefied natural gas in temperatures colder than anything on our planet. Titan is the only world besides Earth known to have stable liquids on its surface. But the liquid part is where Titan becomes truly alien. Imagine standing next to a lake that smells faintly of gasoline, with waves of liquid methane lapping quietly at a shore made of frozen sand-like grains. This isn't water, but it behaves like an ocean in its own way. It rains, it flows, it evaporates, it forms clouds, a complete methane cycle that mirrors Earth's water cycle. But Titan doesn't stop there. Beneath its frozen crust, perhaps 50 to 100 kilometers down, scientists believe there's another ocean, a more familiar one, a possible mixture of water and ammonia kept liquid by internal heat. This makes Titan a kind of double ocean world, exotic methane seas above, and a more traditional ocean hidden below. Water below, hydrocarbons above, two entirely different liquids shaping one moon. The only way we truly learned what Titan looks and feels like up close is thanks to one daring mission, the Huygens probe. In 2005, it became the first and only spacecraft to land on a world in the outer solar system. As it drifted down for 2 hours through Titan's thick atmosphere, Huygens captured images of layered haze, cloud structures, and shifting winds. And when it finally touched down, it revealed a surface that looked surprisingly Earth-like, rounded pebbles, a landscape shaped by flowing liquid, a soft but solid ground. The landing wasn't dramatic. It was slow, gentle, and strangely peaceful. Through Huygens and Cassini, scientists discovered something remarkable. Titan is full of organic molecules. Complex carbon-based compounds are everywhere, in the atmosphere, on the surface, in the lakes. They form naturally under Titan's unique chemistry, almost like a giant laboratory for prebiotic chemistry. On Earth, organic molecules were a key step toward life. On Titan, they seem to fall from the sky like dust. But here's where things get tricky. Titan's surface is far too cold for water-based life. Its methane lakes are around minus 180 degrees Celsius. Any Earth-like cell would freeze instantly. So, could life exist in those lakes? Possibly. But it would be life built on chemistry we don't understand yet. Life that doesn't use water. Life that metabolizes with hydrocarbons instead of oxygen. It's speculative but fascinating, because Titan forces us to expand our idea of what an ocean world can be. When we say ocean, we picture Earth, blue water, salty waves, a surface we can sail across. Titan challenges that picture. An ocean doesn't have to be made of water. It can be methane, ethane, or something yet undiscovered. It can flow on the surface or hide beneath kilometers of ice. Titan blurs the definition so much that it becomes clear. Maybe what matters is not the liquid itself, but the environment it creates. Titan also gives us something deeper, a glimpse of what early Earth might have looked like before oxygen filled the atmosphere. The haze, the chemistry, the organic reactions. It's all strangely familiar and wildly alien at the same time. And the best part? We're going back. NASA's Dragonfly mission, a nuclear-powered drone, will fly across Titan's dunes, riverbeds, and plains, studying its chemistry up close. It's one of the most ambitious missions ever planned, and it could teach us not only about Titan, but about the origins of life itself. By the time you step back from Titan and return to the bigger picture, you start to notice a pattern. Europa with its deep global ocean, Enceladus spraying warm, mineral-rich water into space, Titan with its methane seas and underground water layer. These worlds show that oceans come in many forms: warm, cold, salty, chemical, deep, shallow, hidden, exposed. And every version tells us something about how life might arise. But here's the exciting part. What we see in our solar system is only the beginning. Beyond our sun, orbiting distant stars, there are worlds that make Europa, Enceladus, and Titan look almost ordinary. Worlds that may be covered entirely by global oceans. Worlds wrapped in steam. Worlds where water never meets land. Worlds we've never seen, but whose atmospheres whisper hints of liquid seas. In the next part, we leave our solar system behind and explore the strange and fascinating ocean worlds that orbit other stars. When we talk about oceans in the universe, it's easy to stay close to home: Europa, Enceladus, Titan, and a few other moons where we've gathered real measurements. But the moment we look beyond our solar system, everything opens up. Suddenly, we're not talking about a handful of ocean worlds. We're talking about thousands of possibilities, each orbiting a different star, each with its own chemistry, temperature, and potential for liquid water. To understand how astronomers detect oceans light years away, you don't need to get into complicated equations. The basic idea is surprisingly intuitive. Light carries fingerprints. When a planet passes in front of its star, a moment called a transit, a tiny bit of starlight filters through the planet's atmosphere before reaching our telescopes. And that thin ribbon of filtered light contains chemical clues. Water vapor, for example, absorbs very specific wavelengths of light. So when scientists look at the starlight spectrum and see those wavelengths missing, it's like seeing a little note that says, "Water was here." This technique, called transit spectroscopy, has become one of the most powerful tools for studying exoplanets. It's how we've detected atmospheres on distant worlds. It's how we've identified hydrogen, methane, carbon dioxide, and even hints of clouds. And in some cases, it's how we've detected signs of water. Not puddles on the ground, of course, but water vapor high in the atmosphere, drifting through an alien sky. But the truly mind-bending part is what those observations imply about the worlds themselves. Some exoplanets appear to be water worlds, planets where oceans don't just cover the surface, but extend down hundreds of kilometers. Imagine Earth, but with no continents at all, no islands, no rocky ground to stand on, just water from pole to pole, so deep that the ocean floor lies far beneath crushing pressure. We think a few super-Earths, planets bigger than ours but smaller than Neptune, may fit this profile. Take a world like this, larger than Earth, with stronger gravity pulling water downward, forming an ocean that could be 100 kilometers deep or even more. Under that depth, pressure becomes so intense that water transforms into exotic forms of ice, like Ice 6 or Ice 7, solid phases that only exist under enormous pressure. So, picture this: a global ocean with liquid water on top, but with layers of solid, high-pressure ice below. And beneath that ice, possibly a rocky mantle generating heat. It's not the kind of ocean we're used to, but it's still water, possibly warm in places, possibly mixed with minerals, possibly stable for billions of years. And then there are mini-Neptunes, smaller cousins of Neptune, that have thick atmospheres and perhaps warm oceans underneath. These worlds aren't quite gas giants, but not quite rocky planets either. For a long time, astronomers thought they were simply too gaseous to host oceans. But new models suggest that some may have deep layers where temperature and pressure combine just right to form vast liquid water oceans. These oceans wouldn't sit on a solid surface the way Earth's do. They'd float between layers of gas above and high-pressure ice below. But they would still be oceans in the truest sense. Even more surprising is the idea of subsurface oceans on rogue planets. Planets floating through space without a star. It sounds impossible at first. How could a world without sunlight have liquid water? But sunlight isn't the only heat source in the universe. A planet with a warm core, covered by a thick insulating crust, could hold an ocean under ice, just like Europa or Enceladus, even in the darkness between stars. These rogue ocean worlds might be more common than we think. In a galaxy with hundreds of billions of planets, even a small fraction drifting freely with hidden oceans would mean millions of watery worlds wandering the dark. The more we look, the more evidence we find that water, especially subsurface water, may be the rule rather than the exception. Even planets that seem dry on the outside could hide oceans underneath, kept warm by internal heat or tidal interactions with nearby planets or moons. All of this leads to a simple but profound realization. Water might be one of the most common substances in the universe. Think about how different that is from what we used to believe. Not long ago, people imagined that other planets would be mostly barren rock or gas. Oceans felt like an Earth-only phenomenon, a lucky accident. But now, the more exoplanets we study, the clearer it becomes that water is everywhere, in comets, in planetary disks, in the atmospheres of distant worlds, and in the hidden layers beneath icy surfaces. And if water is everywhere, then maybe life is too. Because life, at least as we know it, doesn't need continents or blue skies or warm beaches. It needs chemistry, it needs stability, and it needs liquid, all of which can exist on worlds very different from Earth. Somewhere out there, an exoplanet's deep ocean might be filled with simple microbial life, or something more complex, or nothing at all, just quiet water waiting for the right spark. We don't know yet, but every discovery suggests that the universe is far more creative with oceans than we ever imagined. And as we reach this point, looking at a cosmos where water seems to appear on moons, planets, and even worlds drifting alone, it becomes clear that the search for life isn't just about Earth-like planets anymore. It's about ocean worlds in every form. In the final part of this documentary, we bring everything together: the water we know, the water we've discovered, and the water we still haven't explored, and reflect on what it all means for us. Because if water is everywhere, then maybe the story of life is a universal one, waiting to be found in places we've only just started to imagine. When you think about where life on Earth began, it almost always leads back to a single place: the ocean. Long before forests, long before insects, long before creatures set foot on land, there were only ancient seas stretching across a young planet, warm, blue, and alive with chemical possibilities. For billions of years, Earth was nothing but an ocean world. Every species alive today, including us, traces its lineage back to that water. It's funny to think about now, because for so long, we believed Earth's oceans made us unique. We imagined our world as a rare exception, a lucky planet with liquid water in a universe full of dry rocks and gas giants. But over time, the more we looked outward, the more that picture changed. First slowly, then all at once. Now we know Earth is not alone. It's just one stop in a much larger family of ocean-bearing worlds. Europa, with its deep global sea beneath bright ice. Enceladus, spraying warm, mineral-rich water into space. Titan, with methane lakes above and a hidden water ocean below. And beyond our sun, exoplanets with steamy skies, global oceans, thick atmospheres, and frozen crusts hiding warm seas inside. Instead of being the exception, oceans might be one of the most ordinary things in the cosmos. And that changes the question. We no longer ask, is Earth the only ocean world? Now we ask, how many ocean worlds are out there, and which ones might be alive? For the first time in human history, we're actually preparing to find out. In the next decade, a new generation of missions is heading to the outer solar system, each one designed to probe the oceans we've only glimpsed so far. The Europa Clipper will orbit Jupiter and perform dozens of close flybys of Europa. It will scan the icy crust, measure the depth and salinity of the ocean, look for chemical signatures on the surface, and try to confirm whether plumes are truly erupting into space. It won't land, not yet, but it will map Europa with the kind of precision we've never had before. Dragonfly, a flying drone the size of a small car, will explore Titan's surface. It will hop from dune fields to ancient riverbeds to organic rich plains, tasting the chemistry of this strange world up close. Imagine a robotic quadcopter drifting through Titan's hazy orange sky, landing wherever curiosity points it. It's one of the most ambitious missions ever attempted, and it's aimed directly at understanding prebiotic chemistry in an alien environment. Then there's the proposed Enceladus Orbalander, a mission that would orbit Enceladus, study its plumes in unprecedented detail, and eventually land near the South Pole. Because Enceladus doesn't hide its ocean, it hands it to us. A spacecraft could literally fly through a geyser and collect samples of an alien sea. If life exists there, this mission could be the one that finds it. And behind all of these missions is an even bigger idea. One day, humans may send submarines into the oceans of other worlds. NASA has already designed concepts for robotic submersibles that could melt through Europa's ice or dive into Titan's methane lakes. Engineers are sketching out drills, heated probes, and miniature flyers that could travel through plumes or glide beneath ice ceilings. These ideas aren't science fiction anymore. They're early steps toward exploring oceans far beyond Earth. It's strange, isn't it? For thousands of years, humans explored Earth's oceans with wooden ships and sails, not knowing what lay over the horizon. Now we're doing something similar, but on a cosmic scale, sailing into the unknown, except the unknown is millions of kilometers away, wrapped in ice and darkness. But that's the thread that runs through our entire history. We explore, we question, we look beyond the next wave, the next frontier, the next world. And when you really think about it, our fascination with alien oceans makes perfect sense. Oceans are the places where life feels most at home, even if life isn't always in the form we expect. Liquid is comforting. It represents possibility, stability, chemistry, motion. And when we imagine oceans on faraway worlds, it's not just curiosity about water, it's curiosity about ourselves. Because if water shapes life on Earth, what might it shape elsewhere? Could there be microbes drifting through Europa's depths? Could alien chemistry be unfolding in Titan's methane lakes? Could warm hydrothermal vents on Enceladus shelter simple organisms clinging to heat in eternal darkness? Could entire ecosystems exist on worlds we've only seen as tiny dots of light? We don't know yet, but we're getting closer to finding out. And that brings us to an important realization. Even across light years, oceans make the universe feel familiar. A global sea beneath Europa's ice might be pitch black and silent, but the idea of an ocean is something we recognize instantly. A world with hidden water feels less like a stranger and more like a distant cousin. In the end, our search for ocean worlds is not just a search for water, it's a search for reflections of ourselves, not in landforms or atmosphere, but in the quiet persistence of liquid, the ingredient that shaped our origins and may shape countless others. This documentary began with something simple, a glass of water, something ordinary, easy to overlook. But now, after exploring oceans across moons, planets, and distant exoplanets, that glass feels different. It feels like a small reminder that we come from water, and that water might be the universe's favorite way of creating life. And if that's true, then the cosmos might be full of life waiting in the dark in places we've only just learned to imagine. Curiosity is the current that carries us forward. From our own oceans to the icy shells of Europa, the plumes of Enceladus, the hazy skies of Titan, and the distant water worlds circling other suns. The more we explore, the more we understand that we might not be the only ocean people out there, just the first ones looking.